Sometimes you may hear about something called a nested for loop. What exactly is a nested for loop? A nested for loop is one that uses one or more for loops inside of another for loop. So you can actually have double for loops, triple for loops, and so on. So here is some pseudocode to illustrate how you might implement a nested for loop. So we have our outer for loop, which is based on the iterator I. And for I in our I vector, we have our open and closed curly braces. We want to execute some code. So we might have some code right here, and then we start a second for loop inside the previous for loop, where in this case, we're going to have our for loop have an iterator j, and for j in this vector of values, we execute some other code. Inside that loop, we have a third loop based on an iterator k being in a vector of k values, and that loop can also execute some code. So the outermost loop is iterating over I, the innermost loop is iterating over k, while the second loop in the middle is iterating over j. This innermost loop based on k is going to be running the fastest. So for each value of j and each value of I, we run every single value of k in that for loop. The second loop that depends on j is going to run the second fastest. It doesn't run quite as fast as k. In fact, for each value of j, we run the entire for loop based on k, but it's not as fast as the outer loop based on I, because for each value of I, we're running the entire loop for the different values of j. Naturally, the outermost loop is going to run the slowest because all of the other loops actually go through a complete cycle before we increment our value of I to the next value in our I vector. One of the things I want to point out is that it's actually really important to properly format your loops, especially when you have nested loops. So always make sure that you're indenting code inside of your loop to make sure that you understand which code is associated with which loop. To illustrate using a double loop, we're going to compute the distance matrix for a set of coordinates. Recall that if xi, yi, and xj, yj are two pairs of points, then the Euclidean distance between those 2 points is computed as the square root of xi minus xj squared plus yi minus yj squared, and we're going to call that entire value dij, the distance between observation I and observation j. So we're going to compute the distance matrix for a small set of 5 coordinates. So I use the cbind function to combine this vector of x values and this vector of y values into our 5x2 matrix. Each row of the chords matrix represents a different location, and for each row of chords, what we're going to need to do is to iterate over all the locations in chords. So for each combination of locations, we need to use equation 1, this equation up here, to determine the distances between the two different locations. So to start out, we need to create a matrix D to store our distances in. We don't want to create this inside of our loop. It's going to be very inefficient and probably create errors. So we create a matrix D where the number of rows in my matrix is the number of rows of chords, and the number of columns in my matrix is the number of rows of chords. And so in this case, it's going to be a 5x5 matrix. And now we have our double loop here. So we have our outer loop that depends on I, and I is going to be related to the current row that we're computing distances for. We want I to run from 1 up to the last row of the chords matrix. And for each value of I, we're going to iterate j also between 1 and the number of rows of chords, because we want to compute the distance between each observation I and every other observation in our data set, including the observation itself. So we start at the first row and go through the last row of our matrix chords. So for our inner loop here, we have the second set of open and closed curly braces. And for row I, column j of our distance matrix D, we are going to compute the square root of the ith row of chords, position 1, or column 1, and that's going to be the x value associated with the ith observation. And we're going to subtract from that the jth row of the first column of chords, which is going to be the x value for the other observation that we're considering. And we square that difference We square the difference between those two x values. And I do the same thing, except that instead of using the first column, I'm going to use the second column, because that's going to do the same thing for the y values. So I sum those squared differences, and then I take the square root of that sum, and that's going to give me the distance between observation I and observation j. And then after I run my double loop, I'm going to print the resulting matrix here. Unsurprisingly, the diagonal elements are 0 because the difference between each observation in itself is going to be 0. But then the distance between observation 1 and observation 2 is 5.83 units. Between observation 1 and observation 3 is 6.08 units, and so on. Just to make sure that we did our computation correctly, we can compare our output to the output of the distance function. So I use the dist function, I give it the chords matrix, and that's actually going to give me the lower diagonal matrix of the matrix of distances. And so to get the complete 5x5 matrix of distances, I have to use the as.matrix function. And when we do that, we see that we get the exact same output from the dist function as we got from our double loop.